Hey guys, welcome back to another video. This time we're going to do another GCSE physics paper because last time a lot of people found it useful, and so I decided I'd do a couple more. So we're going to do GCSE physics paper 1, and this is 2021. So that should be nice and fun. But before we get started, if any of these videos that I've ever done have ever been useful to you, I would ask that you just please subscribe. It really helps me out and it makes my life a lot easier. If you want some information on my tutoring and my classes and things like that, I have spaces for GCSE maths and A-level maths, so you can visit my website, which is in the description, and also my email address is there in case you want to ask any questions about anything at all. If you want to send me questions that you want help on or whatever, that is also in the description. But without further ado, let's jump into GCSE physics. Figure 1 shows an electric car being recharged, and yeah, perfect. The charging station applies a direct potential difference across the battery of the car. What does this mean? So you can say a few different things for this one. One of which is that the polarity of the supply doesn't change. Polarity of supply doesn't change. Or you could say, which I think is the more human way of saying this, it's simply that the potential difference is in one direction only. So if you remember, when you have a direct potential difference versus a alternating potential difference, there is a difference between that. A direct potential difference, it always stays positive. The electrons or the charge, whatever you want to call it, will flow in one direction only, whereas with an alternating, it's being pushed backwards and forwards. So I think that the better way to probably say this, and again, you only need one of these, is that the PD is in one direction only. I think that's the best way to actually put it. One direction only. So let's see what 1.2 is all about. Which equation links energy transferred, power, and time? Well, the equation that you're looking at is power is equal to energy over time, which means energy is equal to power times time. You can also look at the units, right? So power is joules per second. Time second means we're just left with joules. So it's going to be the third option there. And lastly, the battery in the electric car can store 162 million joules of energy. The charging station has a power output of 7,200 watts. Calculate the time taken to fully recharge the battery from 0. For 3 marks is a hell of a lot of marks. All you need to do is use the equation we literally just did. So we can say P is equal to E over T. So again, this is the amount of energy transferred per second. It needs 162 million joules in total, and it does 7,200 joules per second. So that means the time taken is just energy over power. The number of joules we want, 1, 2, 3, 1, 2, 3, divided by how many joules we can supply every single second. So if you'd like, they add on 7,200 joules every second. How many seconds will it take to get up to 162 million? Get your calculator out. 162.123.123 over 7,200 gives me 22,500 seconds, which is a pretty long time to be honest, but that's just the way it is. And for 3 marks, I think that's pretty damn reasonable. And again, for part 4 and part 5, very similar structure to part 2 and part 3. Which equation links current, potential difference, and resistance? This is Ohm's law, which is V is equal to IR. And then here it says the potential difference across the battery is 480 volts. There's a current of 15 amps. Calculate the resistance. So again, we're using this exact same formula. They've given us the voltage, they've given us the current, and we want the resistance. So V is equal to IR. If I divide both sides by I, just like we do in GCSE maths, we get that resistance is equal to V divided by I. So V in this case is 480 divided by 15, and we don't have to use our brains because of course science is a calculator based exam. So 480 divided by 15 gives me 32, and then the units are ohms, although it gives me the units anyway. So far we've got quite a few marks for some decent formulas and equations and calculations. Okay, now here's where things are going to get a bit more interesting. So different charging systems use different currents. So A has a current of 13, B has a current that's twice as big. The potential difference across both of them is 230 volts. How does the time taken to recharge the battery using system A compare with the time taken using system B? So if you think about it, we can use the P is equal to IV formula, right? Just like we did in the first case. Because if we remember back in the first, actually it was the second part technically, we mentioned that the time taken is equal to the energy required, so in this case 162 million, divided by how many joules per second we have. So how many joules can we give to the battery every single second? What's the power? So in this case, hopefully you can see that the only thing that will affect the time taken to recharge the battery, which is, again, the only thing that affects the time is the power. Now, here it says the only difference between these two charging systems is the current. So I need to think of an equation that links power and current, and of course that's the the power equation, right? P equals IV. This is a very common thing in physics. So physics is just interpreting maths. So again, if I go back to the previous question, the only thing that affected the time taken was the power. Okay, well, how does the power change? Well, if I have a look at this formula, the charging system B has a current that's twice as big, which means the power must also be twice as big, right? Because imagine it, let's say we have P is equal to, 13, and let's say the voltage is just, 230, versus P is equal to 26 times 230, we can see that the one on the right is going to be twice as big as the one on the left. Does that make sense? So, what does that mean? Well, if P is twice as big, well, look at this formula here, then that means we're dividing by something that's twice as big. It means the time will be half as much. So the time taken for system B should be half system A. So which one says that? Well, A is half of B. It's not that one. That's saying the opposite. Time taken of A is the same as B. It's not that one. Instead, it must be the time taken using system A is double that of system B, which is the same as saying it takes half as much time for system B than it does for system A. So it means the exact same thing. But hopefully that makes a bit of sense. Here's one of my favourite topics in physics, because this is actually what a big part of my degree was on. So energy from the sun is released by nuclear fusion. Complete the sentences. Nuclear fusion is the joining together of blank. Now here's where things get a bit awkward. You cannot say atoms. Now why is that? It's because inside the sun, or inside stars, or even when we do nuclear fusion on Earth, we increase the temperature of these atoms to such a high degree that they actually become plasma, which means they aren't atoms anymore. The electrons are so hot that they are separated from their nuclei, and it's the nuclei themselves that fuse together. So that is a small little point here. So you have to say fusing together or joining together of nuclei, not atoms, because atoms don't really exist in the sun, because it's so hot that they've actually spread out, they've dissipated, they've been broken apart to nuclei and electrons. So they're basically a bunch of ions. During nuclear fusion, the total mass of the particles actually decreases, which is where the energy actually comes from in nuclear fusion, the decreasing of the total mass of all of the individual particles. So when you fuse them together, some of the energy is actually lost, and we lose that as heat and light, which is why the sun is very bright and also very hot, shockingly. Nuclear fusion of deuterium is difficult to achieve on Earth because of the high temperature needed, 50 million degrees Celsius, which is actually hotter than the sun. Electricity is used to increase the temperature of 4 grams of deuterium by 50 million degrees, and we have the specific heat capacity, basically the amount of energy needed to raise the temperature of deuterium. Calculate the energy needed to increase this temperature. Now, because they've given me specific heat capacity, we must be using an equation with specific heat capacity. So which equation has mass, temperature, and specific heat capacity in it? That is the classic E equals mc delta T, or E equals mc delta theta. It doesn't actually make a difference. So depending on your exam board, I know this is an AQA video, depending on your exam board, they might use T or theta, but it's the same thing. And then we just need to sub it in. The only thing we need to be careful of is this is 4 grams. So we need to change that to kilograms by dividing it by 1,000. And if you weren't sure what that is, like if you found it a bit tricky, I would recommend just using your calculator. So it is 4 times 10 to the minus 3 or 0.004, whatever you'd rather use. Again, if you used standard form, you would still get the same answer. It wouldn't make a difference. 5200 is the specific heat capacity, and we're increasing the temperature by 50 million degrees Celsius, which is pretty hot. So let's use yeah, 1.1 billion joules of energy. Yeah, that makes a lot of sense. Yeah, that's quite a lot. So, and again, if you wanted to, you can write it in terms of standard form and you get the exact same answer. So 4 times 10 to the minus 3, just using brackets instead will help you there. I've just realised it's 5200, not 5700. That was almost a disaster. I can't read my own handwriting. There you go. So 1,040,000,000 joules of energy. Yeah, so that should be a 2. In fact, it does look like a 2 now that I think about it. But yeah, okay, not too bad. Let's go to part 3. The idea of obtaining power from nuclear fusion was investigated using models. The models were tested before starting to build the first commercial nuclear fusion power station. Suggest 2 reasons why models were tested. There's like a million different reasons for this. One of which is to make sure it's possible. Because, what am I doing? When we talk about these commercial nuclear fusion power plants, they cost tens of billions of pounds, which, you don't want to build that and then realise it's not possible and then you've wasted all that money. So they need to make sure it's possible first. The other reason is to understand the process better. I'm going to come up with a bunch more just to help you out so you can come up, kind of think of the ones that make the most sense to you. But we need to actually understand what's going on with nuclear fusion, which we didn't initially. So that's a really interesting thing, is nuclear fusion was discovered, long after we discovered processes inside the sun, which is fairly interesting. So it could be also to actually make adaptations. So how are we going to build something where we don't know any of it? We don't know anything about it. It could also be to assess the efficiency of the process. So is it actually going to be economically viable? How much energy are we going to get out for this? To make predictions, to assess safety risks, to assess the impact on the environment. That's a really big one when it comes to producing energy and electricity. And in terms of the model as well, if we do it on a smaller scale or use a computer simulation or something like that, it's a lot cheaper than building the whole thing and then testing it. So we actually can create computer models essentially for free, as opposed to spending billions of pounds on something that we don't even know is going to work, which is, it's a pretty useful thing. Part 4, generating electricity using nuclear fusion will have fewer environmental effects than generating electricity using fossil fuels. Explain one environmental effect. So when they say one, basically you're going to pick an effect and then explain why. So one of which, the most common, is releases CO2, carbon dioxide, which it causes or leads to global warming. That's probably the one that you are most aware of, right? I mean, it's spoken about in the news all the time, it's spoken about in your lessons all the time. But what else? You could say releases particulates, which can lead to global dimming, for example. So particulates are small particles in the atmosphere, which will reflect light away from the Earth, which is not good. It can also cause breathing problems for people with asthma, which is why you actually find that asthma is a lot worse when you live near an airport, because of the particulates from the jet engines on planes, as an example. It can release sulfur dioxide, which causes acid rain, so that's another 2 marks. Releases nitrogen oxides, which can again cause breathing problems, or causes acid rain. But I think this is probably the one that most of you are most familiar with, which, that makes complete sense. Okay, and now we come to our first 6 marker. So we have student A investigating how the current in a resistor R, so this fixed resistor here, at constant temperature varied with the potential difference across the resistor. Student A recorded both positive and negative values of the current. Now the key thing to remember here is that with this variable resistor, we can change what the voltage is, the potential difference, across resistor R is, because voltage will get shared between them. So if they have the same resistance, each of them will get half of the voltage. And then as we increase this resistance, the voltage here will decrease, and as we decrease the resistance here, the voltage here will increase, which is a very important fact. And it says, describe a method that student A could use for this investigation. So remember, they're trying to see how the current varies with the potential difference. So what we need to do is change the potential difference and record how the current is changing. That's what they're saying. So how can we do that? Well, first things first is I would bullet point my answers. I know some teachers say not to do this. I don't know why, because you absolutely should bullet point your answers. But let's say we had this initial situation. The first thing you're going to do is you're going to measure the current in R using the ammeter. Right? That's the whole point of the ammeter being there. We were justifying it. The second step is to also measure the potential difference across R using the voltmeter. Because again, that's the whole point of this being here. Those two steps are essentially what you're going to repeat again and again and again. But before you repeat that, what you're going to do is you're going to change the voltage by changing the resistance on the variable resistor. So change the resistance on the variable resistor, and then measure current and PD again. You're going to repeat this for a range of different resistances. That's kind of the core aspect. So how are you going to get your data? Well, you take the initial data, so as soon as you turn it on, what's the voltage, what's the current? Then you change resistance, what's the voltage, what's the current? Change resistance, what's the voltage, what's the current? And you repeat this again and again and again. And then what you're going to do with that data is really important. You're going to, so far, we've got 4 marks. We get marks for saying how we use the equipment and how we change the actual voltage here. You don't change the voltage by changing the batteries or anything like that. You use the variable resistor because it's more precise. I mean, imagine you had to change it from here. You'd have to have 20 different types of battery? A 1 volt, a 1.5 volt, a 2 volt, 2.5 volt, 3 volt, blah, 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 blah. It's too tedious. Instead, just use a variable resistor. It's the better way to do it. Now, what we're going to do with this information, right? Imagine this, you have a table of 10 different values, 10 different resistances, which means you have 10 different voltages and 10 different currents. What are you going to do with it? It's hard just to look at it by reading. In every single experiment, after you've described how you get the data, you need to describe how you use it. And in 99% of the cases, you're going to draw a graph. So what you're going to do is you're going to say, plot a graph of what? Well, we need to think about what our independent and our dependent variable were. What did we change and what got affected by that? We changed the potential difference over R, and as a result, the current changed. That's the key thing. So the way you'd write that is you plot a graph of current against potential difference, or you can literally say that this is, you don't need to write this bit, PD on x-axis and current on y-axis. Because remember, the independent variable, the one that you change, always goes on the x-axis because that's the one you're controlling, the one you're changing. And in this case, the dependent variable, which is the current, is what changes as a result of that. So the way I like to think of it is, what am I changing? The other thing is the dependent variable. So what am I changing? That's independent. What else am I measuring? That's independent. That's dependent. That's all you need to really worry about. Now, that would give me 5 marks because you also need to give one way of making the data more reliable. And you can say things like, repeat the experiment 3 times and take an average. You can say, well, in this case specifically, turn off, so basically open switch between readings so that the wires don't heat up. Right? Because think about it, if we leave this on for a really long time, our data is going to be affected because as the wires heat up, their resistance changes, which means the voltage across the resistor will change without us changing it, intentionally anyway. But you can always say something along the lines of repeat the experiment 3 times and find an average. That always works. In terms of the part where it says for negative values of current, you can also do that where you can switch reverse connection of R to find the negative values, so reverse all of this, so flip these batteries around for example, whatever you want to do. But that's it. That's how you get 6 marks in this question. So again, how do you get the data? How do you use the data? How do you make it reliable? That's 6 marks. Nice and easy. Student B repeated the investigation, and during the student's investigation, the temperature of resistor R increased. So remember, as you leave the current on, it's going to start heating up. And as a result, well, we'll speak about the result in a second, it then says explain how the increased temperature of resistor R would have affected student B's results. Now, here you normally state what happens and then explain it. But I actually prefer to do it backwards. I like to explain it, then state what happens. So when the temperature increases, that means the resistance of R increases. That's 1 mark. Because what is the temperature doing? The reason why I like to do it this way is I think the problem that a lot of students have is they're trying to think of what happens and then try and explain why. But the thing is, how are you meant to know what happens if you don't know why? You see my point? You kind of need to know why before you need to know what happens, in my opinion, right? So I would rather do the explanation first and then say, well, what effect will this have on this person's results? Well, we drew a current voltage graph. So what would that be? Well, if resistance is constant, that's weird. If resistance is constant, then our current voltage graph will be a straight line through the origin. Because if you remember, the gradient of a current voltage graph gives you, well, technically it's 1 over R, but it gives you resistance, right? So if resistance is constant, then it gives you a straight line. But if resistance increases, then it means that this will not be a straight line anymore. Instead, you're going to get a curve. So you can just say that the IV graph basically imply that it's not going to be straight. Would not be straight, would not be directly proportional, or it would be curved. Anything along those lines will get you the marks. So you're basically implying that it's not straight. So again, it could be curved, not directionally proportional, would not be straight, etc. And again, I personally think that doing the reason and then the effect is way, way easier. Again, in my opinion. Figure 3 shows the scale on a moving coil ammeter at one time in the investigation. What is the resolution? The resolution of anything is the smallest value that you can accurately measure. So what do I mean by that? That's fancy talk. Basically, it's what are each of these worth? That's all it means. So if you get a ruler out, if you wanted the resolution of your ruler, what do the smallest increments represent? What does it go up in? In that case, it might be 0.1 centimeters or 0.5 centimeters or whatever. Depending on if you have a 30 centimeter ruler, a 60 centimeter or a meter ruler, that changes. So all they're asking us is, what did these little increments go up in? Well, it goes from 1 to 2 and it goes up in 5 lines, right? So it goes 1.2, 1.4, 1.6, 1.8, 2. If you really wanted to work it out, it goes up by 1 in 1, 2, 3, 4, 5 lines. So each of them go up by a fifth, which of course if you put on a calculator is 0.2. So each of those go up in 0.2. So the resolution, the most accurate value that you can measure, or sorry, the value that you can actually accurately measure, the smallest value you can accurately measure is 0.2. Because basically it's what are each of these tiny increments going up in. So with any piece of equipment, if they ask you what the resolution is, you'll never be wrong if you think about what do those tiny increments represent. If you know that, then you're all good. So for example, with a ruler, it goes between 0 and 10, and those individual increments go up in ones. Or if it goes from 0 to 1 centimeter, then there's 10 increments, it goes up by 0.1 centimeters each time, which means the resolution is 0.1 centimeters. So again, it's just which value do each of these little lines represent. Student B replaced the moving coil ammeter with a digital one, and he shows the reading. It has a higher resolution than the moving coil ammeter. One other reason why it might have been better to use the digital ammeter throughout the investigation. Well, if we look back here, anytime you have a scale like this, it's prone to human error. Because I might look at this slightly to the side, I might misread it, etc. Whereas if I have a digital thing telling me, there's no risk of parallax error. So you can say less chance of misreading, because that's what we really care about. But also things like, if you want to get fancy, no parallax error. If you want to do A-level physics, you do need to know about parallax error, so that's good. And yeah, if it has a higher resolution, it gives an answer that's closer to the actual value. But that's it for question 3. For question number 4, we are investigating the density of different fruits, as you do. Gives us a bunch of densities. It says the student determined the volume of each fruit using a displacement can and a measuring cylinder. So determines the volume. Which other piece of equipment would we need to determine the density? Well, the density of anything is the mass over the volume. So if we have the volume, we need something to measure the mass. Now, what do we use? Well, you can call it a mass balance. You could call it weighing scales. You can call it pretty much anything, but basically it's something that will measure the weight, the mass of an object. For part 2, write down the equation that links density, mass, and volume. So that is density is equal to mass over volume, as I just wrote. The mass of an apple is 85 grams. Its density is 0.68 grams. Calculate the volume. So if density equals mass over volume, that means density times volume is mass, and it means that volume is equal to mass over density. So we're going to do 85 grams over 0.68, and we get our 3 marks. Nice and easy. So we've got 85 over 0.68 gives me 125 centimeters cubed. How do I know it's in centimeters cubed? Well, if we look at the units that we have grams per centimeter cubed, so that's how we know. For part 4, the student only measured the volume of each fruit once. The volume measurements cannot be used to show that the method to measure volume gives precise readings. Why not? Well, the thing is, we don't know if it's going to be precise or accurate because it's an unreliable reading. So because the reading is unreliable. To fix this, we need to repeat the readings multiple times. If you measure the weight of something, you say, oh, it's this, and then you don't check, how do you actually know it's an accurate value? Which is basically the point that they're trying to make. Question 5 is about the national grid. It comes up all the time. Very, very useful, very, very interesting, well, so to speak. During 1 year, 1.25 times 10 to the 18 joules of energy. So that's 125 with 16 zeros. So that's trillions. In fact, more than trillions of joules of energy, which is amazing, was transferred from the national grid. The number of seconds in 1 year is 3.16 times 10 to the 7. I'm going to add an S on the end because we need the units, of course. Calculate the mean energy transferred each second. So basically they're asking you how much energy per second was transferred. In other words, what is the power of the energy grid? So it's 1.25 times 10 to the 18 all over 3.16 times 10 to the 7. And once again, shove it on the magic calculator and you are basically done. So 1.25 multiplied by 10 to the power of 18 over 3.16 times 10 to the power of 7 is that to 3SF will be 3.96 times 10 to the 10, which is, so basically we're using 39 billion joules of energy every single second, which is absolutely obscene, but it's also pretty funny. So, figure 5 shows a house with a solar power system. So you have solar panels or cells on the roof, and then it goes into a large battery when it's not needed. Perfect. The charge flow through the cable between the solar cells and the battery in 24 hours is 27,000 coulombs. So what is the current? Now, if you remember the definition of current, it is the charge per second. So it's the amount of charge passing a point every single second. So to work out the current, all we need to do is take the charge, which is given in coulombs, and divide it by the amount of time. Now with the time, this should be done in seconds because with current, it is the charge per unit second. So we have 24 hours, times it by 60 to make it minutes, times it by 60 again to make it seconds, and that will be our answer to find the mean current. And this should be a relatively small number. Well, we're going to find out in a second, aren't we? So 24 times 60 times 60. So that's 62. Come on, Mitchell, what are you doing? Yeah, so a number less than 1, 0.31 amps. Actually, you know what? Let's write the whole thing. So you get 4 marks for that. It's quite a lot of marks, but again, I think the main problem with physics is knowing which equation to use and even remembering the equations in the first place. But try and think about what each thing means. So with the currents, for example, I don't necessarily know the equation. Instead, I think to myself, okay, current is charge per unit second. Okay, so it's charge divided by time. So you don't need to memorize it. And it also helps because you don't have to memorize all the equations or know where they are on your formula sheet. At one time, the total power and input of the solar cells was 7.8 kilowatts. So what that means is the solar energy coming in was 7.8 kilowatts. And they're saying that the efficiency was 0.15. So that means 15% of the energy is stored in the batteries. So that's the actual power output. Because, again, as you know, nothing is 100% efficient. So when this light hits the solar panels, it's giving you a certain amount of energy, but only 15% of that is actually being stored or changed into electricity. So all we need to do is literally just take 0.15 of 7.8 and however much, God, words are hard. However many kilowatts that is our useful power output. So it's 1.17 kilowatts. That's the actual amount of energy you get. But that's also every second, which is pretty good. It's pretty good. And now, here comes everyone's favourite questions, where they start asking about the pros and cons of different types of energy. So in your exam, will it be solar? No, it could be solar, wind, or tidal are the 3 main ones. But they could also put you in, let's say, Italy, and say geothermal, as an example. And you need to know basically the pros and cons of every single one. Obviously, the pros with solar is that it's an infinite source of free energy. You just need solar panels and you can gather it. But why is it not likely that electricity in the UK will be supplied by solar? Well, this is an interesting question because they're basically asking you, what is the downsides of solar power? What's the downsides? Well, the first downside is quite simple. It's just the UK isn't very sunny. Excuse me, hello? The UK is not very sunny, which means you won't produce electricity every day or all year round. So in countries like maybe like Dubai, well that's not a country, but you see my point, but in places like Dubai or even Portugal and Spain, they have far more sunshine. And even in places like Croatia and Cyprus, where they have 300 days of sunlight every single year, then you can use solar because you can produce electricity almost every single day. But in the UK, where we have like 10 days of sun in the summer, it's not very useful because we won't produce any electricity on cloudy days. So that's a big one. The next reason is simply, there's loads, right? You could even say like low intensity of sunlight. You could say things like you need a large empty space filled with solar panels. In fact, in the UK we use wind turbines a hell of a lot, and one of the big problems that's happening now, which it's not really talked about that much, but it is in the news sometimes, is how we are clearing out massive areas of land for wind farms, and as a result that disrupts things like nature. So birds fly into them all the time. It disrupts animals that nest, for example. The noise will disrupt otters as another example. But also, people that live on the land or live near it complain about it because obviously we're taking up huge amounts of land with solar panels. You could even say something like low efficiency. And I think this is probably one of the biggest problems with solar is even if we do get a lot of sunlight, we're only getting 15% of it. That's a really low number. That's a depressingly low number. So again, I'm not going to try and get into politics or anything like that, but 2 of these reasons will be pretty good. Again, with low intensity or not very sunny, you can even say things like number of hours of daylight is too low, as an example. which again is a very good point for anyone that actually lives in the UK. Part 6 is all about atomic physics, so things like atomic numbers and mass numbers, and they give us the atomic and mass number of 5 different atoms, so A, B, C, D, and E. And it says how many neutrons are there in the nucleus of atom A. So here is the big difference between mass and atomic number. The atomic number is just the number of protons. Technically, it's also the same as the number of the electrons. So if there's an atomic number of 89, means you have 89 protons, 89 electrons. So the mass number is the number of protons plus the number of neutrons. So for example, a mass number of 234, it doesn't mean you have 234 neutrons and 234 protons. It means protons and neutrons added together make 234. So in atom A, it tells me that the atomic number is 86 and the mass number is 234. That means it has 86 protons plus a certain number of neutrons gives me 234. So the number of neutrons is just 234 minus the 86 protons, because everything left over should be neutrons. And again, it's a calculator exam, so you're seeing me at my most lazy, where I'm just going to enter everything on a calculator. It's 148 neutrons. So again, atomic number tells you how many protons there are, also how many electrons. Mass number tells you in total how many neutrons and protons we have. Part 2, which 2 atoms in figure 6 are the same element? Now here's a really important thing. The element that you have depends only on the atomic number. Basically, it matters how many protons you have. So, for 2 atoms to have the same element, they must have the same atomic number. So what I'm going to do is I'm going to look along here, and I see that E and D have the same atomic number. That means they are the same element. They are just different isotopes. So if you have the same atomic number but a different mass number, it means you have a different isotope. So a different version of the same element. Ooh, decay, my favourite. I love decay. Nucleus B decays by emitting an alpha particle. Draw an arrow on figure 7 to represent the alpha decay. Now the way I do this is I look at the difference. So an alpha particle, for those of you that don't know, has a mass number of 4 and atomic number of 2, because all it is it's a helium nucleus. So when you remove an alpha particle, your atomic number will go down by 2 and your mass number will go down by 4. So here we're going to go 2 to the left because we're reducing the atomic number by 2. Then we're going to go down 4. So again, we've ended up here. So 226 is now going to be 226 minus 4, which is 222. So we end up down here. So the arrow should just go down and to the left. Because again, we've reduced the atomic number by 2, we've reduced the mass number by 4. What is meant by the random nature of radioactive decay? This is a concept that does confuse some students, and honestly I don't blame you. It's not the easiest. But the idea is, if I have, let's say, 100 atoms that I know are going to decay at some point, I cannot tell which of those 100 atoms will decay first. Okay? So, simply put, we cannot predict which, in fact, I'm putting bold, which nucleus will decay next. Another way to say the same thing, which some people prefer, is we cannot predict when a nucleus will decay. So again, if I have these 100, I know one of them is going to decay. I don't know which one's going to decay. I also can't just pick one of those nuclei, and say which one will. So again, imagine I have all these nuclei, and they start popping, right? I can't tell which one is going to decay next. I can't tell which one's going to pop next. It could be this one, could be this one, could be this one, I don't know. But also, if I zoom in to, let's say, this one on the left, I cannot tell you when it's going to decay. I can't say in 10 seconds it will decay. In 100 seconds it will decay. I have no idea. So we cannot tell which one will decay next or when it will decay. That's the key part of the random nature. Cool. So a polonium nucleus decays by emitting an alpha particle and forming lead. So polonium goes to lead plus alpha. The lead nucleus then decays by emitting a beta particle, which is just an electron, and forms a bismuth nucleus. The bismuth then decays by emitting an alpha particle again, forming polonium, back to the original. Explain how these three decays result in a nucleus of the original element polonium. Okay, so here's what we're going to do. Keep in mind, at the moment, we only care about the atomic number of the element. Why? Because remember, the original element means the thing that determines what element you have is your atomic number. This will not have the same mass number as the original isotope, but it will have the same atomic number. So all we're going to do is we're going to trace the atomic number for now. So during alpha decay, the atomic number decreases by 2. Whoops. Actually, again, remember the reason for that. Because the atomic number of the alpha particle is 2. So it's taking away 2 protons. The atomic number is decreased by 2. Now what happens during beta decay? In beta decay, effectively a neutron changes to a proton and an electron. So the electron goes away and the proton is left. So effectively, the mass number stays the same, but the atomic number gets added by 1 because a neutron has changed to a proton. So the overall number of neutrons and protons is the same, but a neutron's changed to a proton, so the number of protons is increased by 1. So during the first beta decay, the atomic number increases by 1. During the second beta decay, the atomic number increases by 1 again. So overall, there is no change to the atomic number, hence the element stays the same. Now if you traced this, the mass number would be quite different because we've lost 4 nucleons overall, so we've lost 4 protons and neutrons. So it's gone down by 4, then it stays the same. So it's the same element, but the mass number is 4 less than it was originally. But that's essentially all that happens. I would follow it step by step and just say what happens. So again, -2 from A, +1 to A, +1 to A. What happens overall? Nothing. In terms of the atomic number. The mass number is going to be 4 less, that's totally fine. Here we get back to electricity, everyone's favourite topic, whatever you want to call it. So a student investigates how the current in a series circuit varied with the resistance of a variable resistor, very similar to the earlier question. And as she does this experiment, this is the results that she ends up getting. So as resistance increases, current decreases. That should make sense if you think of resistance as slowing down the electrons as they pass through something, then of course they're going to move less quickly, which is basically what current is, how quickly the current's moving through the circuit. And it says here, the battery had a power output of 230 milliwatts, which is absolutely tiny. When the resistance of the variable resistor was 36 ohms, we need to determine the potential difference across the battery. Now, because they're giving me power, the equation that comes to my mind is P is equal to IV. There are multiple ways to do this question, but if I use that 36 ohms, what I could do, so this goes up in 2, so 32, 34, 36, 38, 40, so yeah, it does go up in that. If I just read off that point, I get an answer of 0.08 amps. So now I have 230 milliwatts, which is 0.23, equals, I can't remember what I wrote, 0.08 V. So then all I'm doing is I'm dividing it. There are other ways to do this, so you can kind of sub in and get equations for like p equals I squared r is another way you could do it, things along those lines. But I like to keep things simple. They've given us a graph, then there must be some use for it. And in this case, the use is to do this. So 2.875 volts. Again, for 4 marks, I really like that. I think that's a good question. But the student concluded the current in the circuit was inversely proportional to the resistance of the variable resistor. How could we check? Well, if they are inversely proportional, that means as one increases, the other decreases, right? So we have like a seesaw effect. It means that if we take values from the graph and we multiply them, they should give us the same constant. So actually, let's use this one as the first one. We have 36 and 0.08. What do we get when we times those together? Let's see, 36 2.88. Now, if this is actually inversely proportional, then if I let's say half this number, the other number should double. So in other words, no matter what, if we take a coordinate and we multiply them together, they should give me the same value, because any small decrease in one leads to a small increase in the other. So overall, they'll be the exact same. And we have to do this 3 or more times. A little bit annoying, but that is the way it is, right? Let's see, what would be another good one? Let's say... that's not a really good one either. You can literally take any points along here, so maybe doing this point here, because that goes straight onto 0.05. So that is 5246, 56 times 0.05. Did I say 56? Yeah, I did. Which I can already see is going to give me 2.88. And then you just need to pick another value. So when I'm doing this, I would pick values that are right on the corner of one. So let's say this one, for example. You do not need to use the markings that they've done. You can choose anything in between as well, which would be very useful for that question. So, figure 10 shows a circuit with a switch connected incorrectly. Okay. What would happen if you close the switch? What would happen to the current in the variable resistor? Well, here's what you should know. When you're in parallel, so if this is open, right? So that means all of the electrons are going down this way and going this way, which means the current is at its maximum value. If we close this switch, then it means some of the electrons will go down and some of them will go here. So the current will change. Now, how do we tell how the current changes? Well, essentially, a current would go across the easiest path more. So in this case, because there is no resistance in this other loop, all of the electrons will go down the bottom path. Because again, it's harder to go through the middle. So all you have to do is say that, because again we're describing this, the current in the variable resistor is 0 because the resistance in the bottom loop is 0. Therefore, all of the electrons will go down the bottom loop instead of the resistor. By the way, all you'd need to write is this part here. You would not need to write the rest of it. I'm just writing that for your own perspective. But if you imagine it, like imagine you're an electron, you come along and you have a way that's really difficult to walk through, or you have a way that's really easy to walk through. Which one would you choose to go through? Right? You'd go through the one that's easy. And that's essentially what happens with the electrons. They go through the easiest path. For this question, we have all about energy and kinematics and that kind of topic. So we have a toy car in different positions on a racetrack. So at A here, it comes down, does a loop-de-loop, then flies off. Very cool. And here's the toy car and a racetrack, and the racing track can be modelled as a closed system. Why can it be considered a closed system? So first of all, let's talk about what a closed system is. It is a system where energy cannot escape. So no energy is leaving this system. okay? Which means the total energy can be said to be constant. And the reason for that is the total energy of the racing track and car is constant. So again, when you have a closed system, it means energy doesn't escape out from it, which means the total energy of the system is constant and never changes. For part 2, the car is released from rest position at A and accelerates due to gravity, to position B. The mass is given here, the vertical height between those two positions, and the gravitational field strength. Calculate the maximum possible speed of the car when it reaches B. So if we just look back here, for instance, what they're telling me is the height here is 90 centimeters. I'm going to use that in meters because we're scientists, right? At A, when we're holding it in this position, it has a certain amount of gravitational potential energy because it's been raised up 0.9 meters. And that will be given by mgh. Then, as it accelerates down, when it gets to point B, the height is now 0, which means the gravitational potential energy is now 0, but it's a closed system. So where has it gone? It's been converted into kinetic energy. And the reason for that is, well, think about it. When we let go, so if I'm holding it there, there's no movement, so there's no kinetic energy. When I let go, as it speeds up, kinetic just means movement. It's speeding up, speeding up, speeding up. It's gaining kinetic energy whilst losing gravitational potential energy. The energies have been converted into each other. So when we get all the way to the end, the kinetic energy is the same as the initial energy that the entire car has, the initial gravitational potential energy. So if we do mgh quickly, for the initial gravitational potential energy, we get 0.04. There is actually a very fancy mathematical way of doing this where you can shorten this by quite a bit, but I'm not going to go through that in this video. But you can actually do a very cool thing, which if any of you want to do A-level physics, you will do quite a bit. But 0.04 multiplied by 9.8 multiplied by 0.9 gives me 0.3528. That is a very small number, but remember, this is just a toy car. It's not like it's a bullet or something. It's not going to have much energy. And now, half mv squared should be equal to that energy because all of the gravitational potential energy has been transferred into kinetic. How do we know it's all of it? Because its height now is 0. So we'll do mg times 0, which would be 0. Cool, and we have everything we need. So you can rearrange this first. So I'm going to times both sides by 2, and then obviously we have, in fact, hang on, let's do it properly. A half 0.04 b squared equals 0.3528. So that means 0.02 v squared equals 0.3528. So I'm going to divide both sides by 0.02. Whoops. So I'm going to do answer divided by 0.02 to get 17.64. And then we're square rooting it to get our final, our actual speed, which is, so again I'm going to do square root and then the ANS button, which is our previous answer. We get 4.2 meters per second, which is pretty quick, but again it is just a toy car. It's not meant to like break the sound barrier or anything. So I think those values are all reasonable. And for 5 marks, I think that's, I think it's nice, right? Cool, they give us the same thing again. At position C, the car's gravitational potential energy is 0.2 joules greater than position B. How much kinetic energy does the car need at position B to complete the loop? So, that's a really good question. Is it more than, less than, or equal to 0.2 joules? Now, if it doesn't have 0.2 joules of kinetic energy, it means as it goes up, let's put it this way. Gravitational potential energy gets converted to kinetic, right? To go back to C, that kinetic energy is being converted back to gravitational potential energy, and it will need 0 joules of energy to get to point C, right? Because it needs to, part of the kinetic energy is converted into gravitational potential, and it requires 0.2 joules of energy to get up to there, because it's being raised against gravity. Okay, so that means this is obviously not true. It must be one of these two. Because if it's less than 0.2 joules, it can't be lifted all the way up to point C. It will only go up to maybe up to here and then come back down, or up to here and come back down. So is it exactly or more than? Well, if it's exactly 0.2 joules, then by the time it gets to C, it will have no kinetic energy, which means it's not moving. Which means it will go up to C and then drop straight down. So it needs to have more than 0.2 joules of energy. And the reason for this is the car needs to keep moving once it gets to point C. Simply put. You can also say things like, some of its energy will be lost due to like sound and friction and all of that. But honestly, I think this is the best way to word it because we said it's a closed system, so we're going to assume that there's no energy loss. A teacher demonstrates the relationship between the pressure in a gas and the volume of gas, and this is the equipment used. So as you make the volume in the syringe bigger, the pressure should drop, and as you push the plunger in, the pressure will increase. And they put weights on here in order to pull the plunger out by different amounts. The method used is they record the initial volume of gas and the pressure before any weights are attached. They attach a 2 Newton weight to the syringe, and then they continue going until they get to 12 newtons. So what was the range of force used? So, well, they start off with no newtons, no weights attached, up to 12 newtons. One control variable, there's quite a few different ones that you could pick, but I would say either temperature, right, because if you heat up gas, it expands, or the mass of the gas. Those are the two that are probably the most sensible ones. Again, temperature is a pretty important one. When the volume of the gas in the syringe was 45 cubic centimeters, the pressure gauge shows a value of 60 kPa. So we need to calculate the pressure when the volume was 40 cubic centimeters. There are so many ways to do this. But the key point is that pressure times volume should be constant because they're inversely proportional to each other. So if I times those two together quickly, we have 60 kPa, times 45, which again I'm going to use a calculator, I'm just doing it off screen quickly. 60 times 45 is equal to 2,700. Then when the volume is 40, we have P times 40 equals 2,700. So P is equal to 2,700 over 40 kPa. So that's 270 divided by 4, which gives me 67.5. Not bad, right? And lastly, when the volume of gas in the syringe increased, the pressure on the inside walls decreased. Explain why. Okay, so this is essentially asking you, where does pressure come from? And it comes from particles hitting walls. So if you have a big box here, and we view these, the pressure is the force of the collision of these particles with the wall. So why, when there's a bigger volume of gas, so when there's a bigger volume, so when we make this box bigger, why does the pressure decrease? Well, it all has to do with the frequency of collisions. So essentially, there is more time between collisions of particles with walls of container, right? Because think about it, they're traveling a longer distance to hit the wall. This means there is a lower force acting on the walls. Pressure is force over area, hence pressure decreases. So the idea is, because we're hitting the walls less frequently, there's a lower force acting on the walls, which means the pressure is also decreased. Back to the national grid, again, everyone's favourite topic. But it says here that we have some overhead power cables in the national grid. Explain the advantage of transmitting electricity at a high potential difference. So when you have a high potential difference, it means you have a low current. Because remember, P equals IV. The power, the actual amount of energy we have, is constant. So if we increase V, I has to decrease. Because otherwise we could just generate infinite electricity, right? So, why is that important? That's important because less energy is lost to the surroundings through heating of wires. So when you have a high current, and you can actually test this, and if your schools or if your teachers are any good, they would have shown you this. But if you have a piece of wire and you put a low current through it, nothing happens. But as you heat up the wire more and more and more, it starts to get hot, because current leads to heating of the wire, which means you lose energy, right? Like the energy has to come from somewhere. So you lose energy in the form of heat. So since less energy is lost to the surroundings, this increases the efficiency of the wires, or the transmission, whatever you want to call it, because you're losing less energy, which is a good thing. It is dangerous for a person to fly a kite near an overhead power cable. The person could receive a fatal electric shock if it's too close to but not even touching the power cable. And this is actually a really important thing, because there are idiots in real life. There are unfortunate people in real life that have been electrocuted by power cables without touching power cables. And here's the reason. So when you have a high potential difference, the electric field strength, so in fact, alright, high PD means very strong electric field. Okay? This can cause, and by the way, so strong electric fields cause lightning and thunder. They also what cause, those Tesla coils where you can see the electricity going out from this metal thing? That's because there's a very strong electric field. And again, the existence of lightning is because there's a high electric field in the air, and it causes the air to be ionized. So essentially, even if you're not touching the overhead cables, but you're close to them, you can get hit by lightning that comes from the power cables themselves. So this can cause air to become ionized, which is then conducted through the kite and into the person. So even if you're not touching the overhead power cables, if something's very close to it, there's basically a little mini lightning strike between the cables and the metal or the conductor that will then pass through and go straight into you, which will kill you horrifically, because voltage is very, very bad. It'll basically cook you from the inside, which is very exciting, right? I'm kidding, it's not, it's horrible. A scientist investigates how the potential difference needed for air to conduct charge varies with distance between a cable and Earth. And if you have a look at how small this is as well, look, like 0.2 meters, 20 centimeters, is very small. The data gives the relationship between potential difference and distance when the air is dry. When the humidity of air increases, the air becomes a better conductor of electricity. Draw a line to show how this will... Okay, cool. If it's a better conductor, it means it will require fewer volts to conduct electricity. So your line will be basically the same thing, but shallower. So it'll be a less steep line. Now it still goes through the origin. And the reason why it still goes through the origin is because it still will require 0 volts at 0 distance, right? If you grab a cable, it will electrocute you. But here it's saying, even when you're 5 centimeters away, if there is a voltage of 180,000 volts, you can be electrocuted. If you're 20 centimeters away and there's a 600,000 volt, you can be electrocuted. But look at the difference. Like, when it's humid, which, yeah, that happens a lot of the time when it's about to rain, that line becomes shallower, which means fewer volts required to electrocute you, even if you're not touching the wire. Again, this isn't something to be scared of. This is for the overhead power cables, which is also why they're put really high into the air, so that way no one can accidentally touch them and get killed. This is a cross-section through a power cable. You have steel in the middle, surrounded by aluminium. A 1 meter length of a single aluminium wire is a better conductor than 1 meter of steel. Individual wires behave as if they're resistors connected in parallel. Explain why the current in the steel wire is different to the current in the single aluminium wire. So this isn't too bad. The potential difference across the wires is the same. Okay, that's fine. But current in parallel is split between resistors, right? So the potential difference across all of these will be the same, but each one of these cables will get a fraction of the total current. So it says here that aluminium wire is a better conductor than steel, which means steel has a higher resistance than aluminium, which means it will get, so therefore the steel wire will have a greater current because its resistance is higher than aluminium. And when you split current in terms of in parallel circuits, the bigger the resistance, the more of the current that it will get. Actually, just quickly changing this, it should have a lesser current. Sorry, I just have less current. Because again, when you have V equals IR, V is the same. If resistance is higher, it means the current has to go down. So again, I know I contradicted myself earlier, so that would have a lower current. That was a slip of the tongue, that's all it was. Because again, the voltage is the same, potential difference is the same, but resistance is higher, which means current has to be lower to match it, right? So that's all there is to it. So again, apologies for that, but I spotted it a little bit too late. The final question is all about latent heat of vaporization and of condensation, and of melting, things like that. So very, very interesting indeed. So a student investigated how the temperature of a lump of ice varied as the ice was heated. So he recorded the temperature until the ice melted and then the water produced boiled. So as you can see here, it goes up from -50. Wow, that's really cold. Okay. Then up to 0, then it goes flat, then it goes up, then it goes flat for quite a long time, and then it starts to boil. The specific heat capacity of ice is less than the specific heat capacity of water. But how does the figure show this? Well, if you remember what specific heat capacity is, it is the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree. I know that's a lot, right? But essentially, the higher the specific heat capacity, the more energy it takes to raise the temperature. It says the specific heat capacity of ice is less than water. Now, if it takes less energy to raise the temperature, it means the temperature will raise faster. This beginning section here for the first few seconds is when the ice is ice, right? When the material is ice. Then when it melts, it turns into water, and look what happens. Look at the steepness of this line compared to the steepness of this line, right? Because the specific heat capacity of ice is less than the specific heat capacity of water. It takes less energy for ice to increase in temperature than it does for water. That's how the figure shows this. So let's write it out. So the gradient for ice is steeper than the gradient for water. Again, don't forget it says explain how it shows this. So we've stated that the gradients are different. Okay, explain what that means. Exactly what I said. The energy needed to change the temperature of ice is less than the energy needed for water. Again, that's because it's steeper. If it's changing temperature faster, then that means it must take less energy to heat up that substance. The specific latent heat of fusion of ice is less than the specific latent heat of vaporization. So, whoops. What does this mean? This is the energy to melt something. This is the energy to boil. So again, how does figure 17 show this? So we see these two flat parts here. The flat parts represent a change of state. So this is when the ice is melting into a liquid, and this is when a liquid is boiling into a gas. So how does this show that the specific latent heat of fusion is less than the latent heat of vaporization? Well, if we look at the difference, look at the difference. Solid to liquid happens in under 100 seconds. Liquid to gas happens in over 500 seconds. So, in other words, and this is in layman's terms, it takes longer to boil water than it does to melt water. Now, again, think about how we're linking this to the experiment. If it's taking longer, it means it requires more energy to boil water than it does to melt water. To melt ice, sorry. So that's exactly how the figure shows it. Whoops, no, I don't like that. There we are. So, water took longer to boil than ice did to melt. Therefore, more energy is needed to boil water than to melt ice. Okay, and that's how the graph shows that. A second student did the same investigation and recorded the temperature until the water produced boiled, so the same investigation. In the second student's investigation, more thermal energy was transferred to the surroundings. Describe 2 ways the results of the experiment would have been different. So, as they're heating up this, in fact, let me draw it out for you. We have this beaker. We're going to have some kind of... that's meant to be fire, right? Some kind of heater. And in the first case, we have insulated the entire beaker. And so as much of the energy as possible goes into actually raising the temperature of the substance. However, if we had no insulation, how would this affect it? Well, the first thing is, and again, you can imagine when you're cold, right? When you're cold, what happens? Well, your body decreases in temperature, but it also takes you longer to heat up. Don't do this at home, but imagine if your parents put on the heating and you open the windows, right? And it's in the middle of like November, December. What's going to happen? Is the room going to heat up very quickly? No. Why? Because energy is being lost to the surroundings, out your windows. Again, don't do this, otherwise your parents might beat you. But that's the idea that's happening here. We've heated up this thing, but the energy is being lost to the surroundings. So it will take longer to increase the temperature of the ice/water, because it's 2 different states, right? That's the first thing. And again, the same reason why if you turn the heating on at home and then you open up your windows, it takes a long time for your room to heat up, whereas if everything's closed, it takes less time. Okay. The other thing is that you could also say it will take longer for ice to melt and water to boil, because again, it's harder to raise the temperature. In terms of other things that you could say the change in temperature with time would not be linear, but that is, I would be surprised if anyone can think of that, because that's quite advanced. If any of you want to do A-level physics, or even A-level chemistry, we go into that in a little more detail. By the way, you could even say like the gradients would be less steep, or the horizontal lines would be longer. That also works. 5-mark calculation to finish off with. So, when the water was boiling, 0.03 kilograms of water turned into steam. So when the water was boiling, the energy transferred to the water was 69 kilojoules. Calculate the specific latent heat of vaporization. Now, latent heat, or vaporization or fusion, doesn't matter. It's given by the equation M times L. E is the energy required, M is the mass of the substance, L is the latent heat of either vaporization or of fusion. So all we need to do here is sub in the values. So we have 69,000 joules of energy equals 0.03 L, which means L is equal to 69,000 over 0.03. This number for water is going to be very high because it does take a lot of energy to change the temperature of water, which is actually a good thing, because imagine if water could change temperature really easily. What would happen to our bodies? We go out in the sun and we just turn to steam and like blow up or something like that. You know, it wouldn't be very nice. But yeah, 2.3 million joules per kilogram of water is actually about right. So that is perfect. Again, it won't be a perfect answer because this is not a perfect experiment. But what are the units? Well, the units, if we have a look here, if you think about the definition, it's the energy required to change a kilogram of a substance into a different state.
So it's joules, the amount of energy required per kilogram for 1 kilogram. So that's it. 2,300,000 joules per kilogram. And finally we get to the end. That was quite a long paper. An hour and 45 minutes was longer than I expected. I actually thought that the papers were slightly shorter than that. But who knows, maybe I did the wrong paper, which is possible. Because GCSE science is confusing and all the different things it can take part in. But anyways, if you do want me to see me do kind of paper 2 of physics, but also bio and chem, then do let me know in the comments. And remember, please subscribe if you found any of this useful. Visit my website if you're interested in any of the tutoring. And of course, my email is also in the description in case you want to ask any questions or make any requests as well. But other than that, I hope to see you in the next one. Have a wonderful day.